assuming you've seen some of the other videos in the series before this one. This is the second in a series of 4 about key aspects of climate batteries. In this video, I'm going to discuss just the heat exchanger portion of a climate battery. That means I'll focus on the heat exchanger tubes, their length, spacing, and how the heat transfer system works. Then I'll share a few examples of what not to do. Climate batteries store the large amount of excess heat energy accumulated inside the greenhouse during the daytime in the ground below the structure to utilize at night for heating. During the daytime, air blows through a grid of tubes embedded in the ground. As the air flows through those tubes, the heat passes from the air into the ground and around the tubes. Then at night, the air flows in the same direction, but moves the heat from the ground into the growing space. Ground will typically be warmer than a system without a climate battery and warmer than the ground temperature outdoors. Because each of the tubes of the heat exchanger are identical repeating elements, we can do a deeper analysis on just a single pipe to break down the details of how these are functioning. Most illustrations that I've seen of climate batteries are artistic renditions of the heat flow. Let's look at an actual engineering simulation using modern computational fluid dynamics tools. Here I've broken down the heat exchanger to a single tube with its surrounding soil. First, we have 16 inches of soil as though we were spacing tubes every 16 inches. I have it sectioned in half for viewing purposes so we can see what's happening inside. The length of the tube and the soil is 25 foot long. The starting soil temperature around the tube is 50 degrees Fahrenheit, which is a realistic temperature to have in the morning just before we start storing heat as the sun comes up. We're going to blow 90 degrees Fahrenheit air through this tube at 75 cubic foot per minute continuously for 12 hours. 75 CFM is a pretty high airflow rate. Let's start it. Notice how our air temperature decreases throughout the length of the tube as the energy passes from the air to the soil around it. The soil heats the fastest where the air temperature is the highest in the tube and gradually warms at a slower rate farther down the length of the tube. Some key takeaways: faster airflow rates will increase heat storage or withdrawal rates. Longer pipe lengths will need even faster airflow rates to utilize the storage capacity of that length of soil. And closer pipe spacing will allow better utilization of the soil's thermal mass. Let's start off with what pipe size is best for the heat exchanger. More smaller pipes provide more air to soil contact for improved heat transfer rates. However, small pipes are much harder to push air through due to friction, or what engineers call head loss. Here's a graph. On the bottom axis we have the amount of airflow. On the vertical axis we have pressure loss or friction. As the pipe diameters decrease, the pressure drop increases exponentially. So 4-inch pipe brings a good balance between heat transfer and the cost to move air through it. Now that we know we are targeting 4-inch pipe, do we use a smooth or a corrugated pipe? Smooth pipe is $1.70 per foot, and corrugated pipe is 56 cents per foot. That's a 3x difference. Smooth wall pipe would have to be pretty dang good to make sense over a corrugated pipe. There are several papers out there that have characterized the heat transfer rate through these types of pipes. I'll highlight just this one from McGill University in Quebec. In conclusion, they found, quote, forced convection heat transfer coefficients for non-perforated plastic drainage tubes are similar in magnitude to those of smooth plastic tubing of equal nominal diameter but of unequal surface area. However, you must make sure that you use perforated pipe in the climate battery because humidity will condense in the pipe during heat storage, and that water must escape or the pipe will fill up and you won't get airflow through it. Another common question that people have: to use pipe with the sock or not? There is some additional cost for the sock, But most importantly, the sock is meant for water drainage applications where crushed rock with very fine clay soil or rocks with sharp points that can clog the perforations when water is flowing into the pipe. In a climate battery, air is flowing through the pipe, and sometimes air is flowing out of the perforations in small amounts. Do not use the sock. It reduces the heat transfer to and from the soil by adding an insulating layer around the pipe. It also allows a place for moisture to saturate the fabric, causing mold and biofilms to accumulate, affecting the atmosphere within your greenhouse. And it just adds unnecessary cost. So we figured out that we want 4-inch perforated corrugated pipes. Now, how much do we need? Let's look at an end view of a few options to see what a range of tube spacings would look like. All of these layouts are to scale and assume a 4-foot depth. Seeing the number of tubes, it quickly becomes clear that this is a very important and a potentially costly decision. Let's step back to the numerical simulation for a quick refresher. We see that the temperature of the soil is highest in contact with the tube, and it decreases with distance from the tube. Now, let's look at the system from the side, or end view. I'm going to be using the results from a paper published in 1997 called Numerical Simulation of Soil Heat Exchanger Storage Systems for Greenhouses from the University of Sherbrooke, Quebec. Don't worry, I have converted all of these metric units to the archaic imperial units that us Americans love. Here we have an isotherm line view of one of their digital models showing the temperature gradient distribution through the soil around the pipes and across the insulation barrier on the left. I'll overlay the side view of my simulation as well, so you can see a colored version. It is 2025 now, and our computers do have color monitors. This gives me a feel for the level of heat penetration into the soil from the heat exchanger. In their study, they ran 240 different simulations and validated them by comparing to a prior real-world prototype from 1990. They developed data providing a clear relationship between the pipe-to-pipe distance, the length of the pipes, and the airflow rates. As a result of the study, they produced this graph showing some of the trade-offs for a 33-foot long pipe. On the bottom axis, we have the pipe-to-pipe spacings from 8 to 28 inches. The vertical axis is the airflow rate through the pipes, and the numbered lines are the amount of daily stored heat. A key takeaway is how poor the wider spacings are. Not even increasing airflow can make up for it. I've seen some folks in their books recommend 24 inches, and that's plain wrong. I followed those guidelines on my first climate battery. It functioned, but even in early February, when it was quite cold, I could not store enough solar heat fast enough and had to vent the excess heat out of the structure. The smaller pipe spacings just aren't realistic as they become very expensive to bury that much pipe. Pipe spacings around 16 inches bring a good balance of cost versus performance. So really, the recommended tube spacing is about 16 inches. Stepping back to the simulation that I showed you for a quick refresher, we see that the soil heats much quicker at the inlet, where the air in the tube is warmer, which helps explain the pattern that we see in the following data. This graph was also produced by the same study as the previous one. However, now we have the length of the pipe on the bottom axis and the daily heat storage rate on the vertical axis. The airflow rate is held constant at 68 CFM, and the pipe-to-pipe spacing is shown by each line. The recommended 16-inch pipe spacing is shown in green. As expected, a shorter length of pipe will produce a greater rate of heat storage because the warmer air temperature during the length of the pipe will increase conduction rates through the soil. The best practice is to keep the length of the tubes as short as you can. That means you should run it the narrow width of your greenhouse or high tunnel, not the long way. Typically, this will produce a pipe length somewhere around 20 to 30 foot maximum. To begin the discussion on how much airflow is best per tube, let's go back to this previous graph showing the pipe spacing, the airflow rate, and the heat storage per day. In the conclusions of the paper, they recommended about 68 CFM as the optimal airflow target. Why? 68 CFM is nearly optimal. Below this speed, the heat storage efficiency drops rapidly, but above this speed, any extra heat gain is quickly canceled out by the much higher fan power required. Fan power usage increases exponentially with the amount of airflow. So that's all great, but is there even that much sunlight or solar energy available to store in the wintertime here? Let's check it out. I did the math for the geometry of structure that I built with a shape optimized for my latitude to capture and retain sunlight. The structure is a 60 by 27 foot structure like this. The light gray is what's called the clear sky model. This is a theoretical average value, assuming we have clear skies all day long. Dark bars are based on local measured values from 2021. We don't really care about the non-heating months of the summertime. Let's get rid of those. So maybe we have daily totals from 800 to 1750 BTU square foot hitting the structure every day. We likely lose 30 to 40% of that through the double layer of film, which puts it at around 1000 BTU per square foot of structure per day. We have about 7 hours of good strong sunlight for many of the winter months. So we have a good 142 BTU out per hour per square foot to store. I've characterized the heat storage rate from my climate battery for a range of airflow rates, 16 up to 75 CFM per tube. Even with the 75 CFM and starting the day with cold soil, empty climate battery, the 75 CFM flow rate, we have more energy than can be stored, confirming the guidelines to the design for approximately 50 to 75 CFM of airflow per tube. If you live farther south, less airflow is needed because your starting ground temperatures will be warmer. I scoured the web to find pictures of what not to do. It was actually very easy. I have removed any incriminating evidence via AI, so hopefully nobody feels bad. This fella looped his pipes back and forth, making them very long. Don't do this. And again, this example has a similar issue, but even more extreme. He has very narrow pipe spacing, which is good, but the long length of the tube, only one tube here, one inlet and one outlet, will really reduce the effectiveness of the system. In fact, he may not have even been able to find a fan with enough pressure to push the air through this tube. And the sock. Don't do this. This is not a French drain used to transport water. In a future video, I'll review the many ways to get air into the heat exchanger and to size the fans properly. This video was funded in part by USDA's South Dakota Specialty Crop Block Grant. If you enjoyed this video, make sure to leave a thumbs up and share it with your friends. I'd also love to know your thoughts. Comment down below and let's chat. And if you haven't already, be sure to subscribe for more content like this.